Programming Throwdown, episode 120, Machine Learning Embeddings with Edo Liberty. Take it away, Jason.
Hey everybody, how's it going? I know a lot of folks out there ask about AI and machine learning. Patrick's done some machine learning stuff in the health space. I do a lot of machine learning stuff, or at least I pretend to, in my day job. And so a lot of people write to us, message us on Twitter asking questions along these lines. And so it's always a real pleasure when we can talk about, kind of an area that we really love. And this is right in the heart of it. We're going to be talking a lot about machine learning embeddings, which is a term you might not have heard before, but you're going to really enjoy it. And it's something that is extremely, extremely useful. I'm extremely lucky that we have Edo Liberty here, who's an expert in this area. He's the CEO of Pinecone, and he's here to talk to us about embeddings and kind of riff on that. So thanks so much for coming on the show, Edo.
Yeah, thanks for inviting me, guys.
Cool. So we ask a lot of folks this lately. How has COVID kind of changed your business? Are you back in the office yet, or what's going on with that?
We half are and half aren't. So the California folks are still at home. New York folks are back in the office. Israel folks are back in the office.
Oh, I see. Is that because of local laws or just how people felt in those areas? Or
It's a bit of both. A bit of both. I'm a big believer in people hanging out together and seeing each other and having lunch together and getting to know each other a little bit better than on Zoom. So I'm pushing everybody who wants to be together to be together.
Yeah, totally agree. I wonder if we'll end up with, remember WeWork? I think, is WeWork still a thing? It probably is still a thing, even though they had all sorts of issues as a company. But that might be the kind of thing where physically you're next to a bunch of people that you can socialize with, but you actually all work for different companies or something like that. Who knows what the future is going to be?
Yeah, 100%.
Cool. So yeah, why don't you tell us your story and how you kind of got into this area and how embeddings became important to what you do and kind of where that all started from.
Yeah. So my journey into becoming a CEO has nothing to do with business. I did my PhD in computer science and my postdoc in applied math, working mostly on CS theory and algorithms for machine learning and big data. And what I ended up doing mostly was high dimensional geometry, so numerical linear algebra and clustering and dimensional induction and stuff like that. And a big part of that was nearest neighbor search and searching through high dimensional vectors, which we will get to in the end, or in the middle of this discussion. And then I opened a company in 2009 that did real-time video search. And real-time video search kind of has to be based on this vector search capability, which we'll talk about later. And again, so I started investing in that.
So can you tell me real quick, this always fascinates me, how did you make that leap to being an entrepreneur? So right before, let's say 2008, what were you doing? And then were you able to sort of quit that job and say, okay, I'm going to start this real-time video understanding company? What made you take that leap of faith?
So the answer is, that it's two things really. One of them is I've just always kind of been very entrepreneurial, but by nature, I was importing like balance skateboards to Israel when I was in high school, and I was always like doing stuff like that, right? So some part of it was always a little bit entrepreneurial, but the other one is just like dumb luck and just happenstance. I was in New York, and my cousins of all people said, "Oh, I'm going to start this company, and I'm going to hire, whatever, like 10 engineers to do X, Y, Z." And I'm like, "Oh, you don't need 10 engineers for this. We can whip it up in like like a month, and you can go raise money on that." And he didn't believe me, so we spent a month and we made something work. And so when we found ourselves with some money in a company, so like, okay, I guess we have to run a company now.
Wow. So you took a month off, like a month. I wouldn't call it a vacation. It's probably like the busiest month of your life, but you took that month off, quote unquote. And then you went to investors and you said, here's our idea.
I was a postdoc at the time. So it's like the work was not incredibly demanding, definitely not time critical. So like I could kind of disappear for a month. It was actually a great, like I loved it. I actually still remember it. I would wake up at like 8 a.m. I would make myself coffee. I would sit down and I would code until like midnight and go to sleep. I did that for a full month, and it was fantastic. It was fantastic.
It's so addictive. It's like this dopamine rush, you
Yeah,
know?
exactly. I didn't talk to anyone. I didn't need anything. I would just like drink coffee and code for like a month straight. It was fantastic. I loved it. Not a single meeting.
Man, it sounds amazing. Actually, you bring back really, really positive memories. I mean, maybe we should do that again. I mean, like every now and then, maybe.
Highly recommend.
Yeah. Wow. That's an awesome story.
A month worth of flow. It was fantastic. But anyway, the cool part about it is that we end up building a really cool solution. We end up selling the company. I moved to Yahoo and I was there, director of science.
So did you sell the company to Yahoo, or was that how it worked out?
No, we actually sold it to Vizio,
Ah, okay, got it.
the TV company, and then I moved to Yahoo, where I spent a lot of time as the director of machine learning. So I was building machine learning platforms and solutions and so on, working on mail and ads and spam and feed ranking and so on. And yeah, then I went to AWS and spent about 2.5, 3 years. So all the offerings from AWS, so SageMaker and all the
There's like recognition, I think, for video.
yeah, exactly all the image stuff, language stuff, all that all those services. I didn't own all of them, but I was definitely a part of building that org and being a big part of the science of a lot of these services. So my journey has kind of been a little bit all over the map, which is highly recommended. Seems chaotic in hindsight, but kind of fun nonetheless.
No, I think it's amazing. I think it's great. I think that, you can see the progression. I mean, it might seem chaotic, geometrically, but you can see kind of a nice trajectory.
Yeah, yeah.
Very cool. And so you were at AWS, and then from AWS, is that how you were inspired to go to Pinecone, or was there a spot in between?
No. From AWS, and I opened Pinecone. So it was kind of seeing how the sausage is made, like building managed services and databases. That's where I really got into like databases and managed services and cloud offerings and so on, kind of really diving in deep into that. And it suddenly dawned on me, that like I have solved exactly the same problem like 10 times in my career. And I always built it from scratch. And it was always hard and always like insufficient in the end.
Yep.
So I figured we should do it once and for all and like do it right and give it to everyone.
Yeah, that's awesome. Very, very cool. Yeah, fascinating. Yeah, I think it's an amazing journey. We can now give kind of an overview of, what that means to, provide sort of a vector database. And so maybe we first need to talk about embeddings and where do they come from and why we need them.
Yeah. So one of the interesting statistics that kind of I uncovered while thinking about opening Pinecone. Okay, I had a lot of conviction that this was needed, but like I knew embeddings were needed for dealing with unstructured data. So when you look at like tabular data, it's very clear how to store it, how to slice and dice into it, how to work with it, because we have like 50 years worth of databases developed for it.
Yeah, I mean, if people have used Excel and you've done this thing where maybe you have a bunch of columns with data in Excel, and then you want to try to learn a new column, like there's a column that has some missing values, and you want to try to guess it from the other columns. That's pretty easy to do in Excel, and you can kind of imagine what's going on there. There's some model that's just looking at a single row and pulling those values and then trying to infer that new column. But then there's a question of like, how do you do that if it's an image or a video or a website? Now it's totally unclear how to do that.
Correct. And this, it extends much more. So it could be like, yeah, those like very complex data types like images and long text documents and, some like audio recordings and so on. But it could be like travel through a website, like a trajectory through a website or a shopping cart or something else, which is in and of itself like a complex object. It's not something you can stick in a table in like four columns, right? And for a long time, it wasn't really clear how to deal with those objects, right? It was like each and every one of them had its own like little mini discipline in computer science on how to reason about them, how to structure them, how to predict about them, and so on. And in the last few years, there has been this movement with deep learning to basically unify this entire paradigm. So basically say, I will use deep learning neural nets, basically, like deep neural nets, right? To take the input in some way and transform it through some layers or through some transformations, and in the end provide a high dimensional dense vector. So let's say 1024, or an array of 1024 floating point numbers. But I will train the network such that that vector is somehow semantically representative of the object. For example, I would train it such that if two documents mean the same thing, okay, they talk about this in topical, they're similar in some sense, then their resulting vectors would be very correlated.
Yeah, and then the magic is knowing what that similarity is, right? Or how to measure that.
Right. And so there's a whole, again, there's a whole body of literature and a good amount of like technical know-how of how do you take data and produce these embeddings such as they are good. But the fascinating thing is that while it isn't always the perfect solution, it's very often great. And so you can transform images and text and audio and like shopping habits and like your video preferences and like pretty much you name it, and convert it into this like dense vector. Okay, and now you can, instead of dealing with these complex types, you can now have this embedding. This you actually you embed, like you by embedding, it's like you put an item in high dimensional space. You assign a vector to it, right? So think about a vector as like a point in a high dimensional space. That's why it's called embedding. And so now, instead of talking about documents and semantic similarity, you talk about vectors like and angles and distances. And so now it becomes a lot more concrete and a lot more actionable and a lot more something that you can reason about and like build for in like code and systems, and not like it's not an abstract thought anymore.
Yeah, I mean, if people have seen this visualization where there's a bunch of points and they all have kind of springs in between them, and then you run this through some physics model, and they all just kind of separate and they end up in this like spider web kind of shape, right? That's because all the points are kind of repulsing each other. And even though it's only a local repulsion, it creates this really beautiful kind of spider web structure globally, right? Because you see this similar with birds, right? Birds have a similar thing where, they have some very simple rules in their brain around not getting too close to other birds and like staying in a certain position to the bird next to them. And then that ends up with this like beautiful kind of V shape or swarm or things like that. And this is similar where we're doing that, but then some of the points are actually getting pulled together and some are getting pushed apart depending on things we know about them.
Exactly. So there were like works from, I think, the early 2000s called like self-organizing maps. Or maybe this is like idea is even older. I don't know. Maybe the idea itself. Actually, you know what? I think the idea itself is even older. There were like old works like on MDS, stuff like that, and ISO maps, and there was like a flurry of works in that regard. So you would like take things like, say, I'll take all the people, like a million people, and I'll just look at their social network graph,
Yep.
and I'll try to create like these virtual springs that put people that close together, right, physically, right. So then we'll try to make them like physically adjacent to each other. And if you try to do that in two dimensions, what you get is the map of the US, like if you have on the US folks, right? Maybe now with COVID and social networks, maybe that now doesn't work anymore. But back in the day, it did.
Yeah, or if you imagine doing a two-dimensional embedding on interests, you might have like a little island over here of gamers and a little island of skateboarders, And there might be somebody who's interested in both. And so they're going to be kind of on this sort of inflection point or on this saddle point in between those two clusters. But you'll still have those large clusterings, or maybe you'll have another cluster of gamer skateboarders, right? If there are enough of them, and that cluster will start having a defined border and pushing the other clusters away. And so, Jay, you end up with these really beautiful behaviors. And when you're done, you have something really interesting. You can draw a little circle on that map and say, everyone here really likes skateboarding. And once you start introducing a whole bunch of other topics and you get to more than 2 dimensions, you can even guess at things that people like that they didn't even know they liked.
100%. And I think in 2 dimensions, you get pretty limited pretty fast. So 2 dimensional space is very limited. But when you live in a 1,000 dimensional space, you get so much more representational power, because you can be a skateboarder, but in the same time be a dad, and at the same time be like really into like whatever, like anime and whatever, like also be like vegetarian. I mean, and all these things are facets in your behavior and things that you care about, and they're not mutually exclusive, and they're just like a part of you. So you're not a skateboarder or a vegetarian. You're both.
Yeah.
So that's how these high dimensional dense vectors can actually like represent something a lot more deep, a lot more rich, a lot more actionable than just like this one feature or another.
Yeah, it's that curse of dimensionality, but actually working in your favor, where going from 2 to 4 dimensions gives you so much more expressibility, and then going to 1,000 dimensions gives you exponentially more expressibility, and it's just amazing what you can represent. I mean, we've seen just unbelievable things with GPT-3, where people have auto-generated websites. There's this thing Codex where it auto-generates code, and I mean, it's just amazing, and it's all using embeddings.
Yeah. And the amazing thing is like that's how our brain works too.
Yep.
Right. So if you think about everything that you remember seeing, okay, everything that you've ever seen, okay, the part of you, the lateral cortex, I mean like pretty much everything your higher functions in the brain that deal with visual imagery, okay, the input that they have is not the light intensity on your retina, which you might think is highly related to the actual like image, right? Or what's like what we think about is an image in like as a RGB raster, right?
Mm-hmm.
What your brain gets is the output of the visual cortex, which is an activation of a few million neurons, right? And that's it. Like and those activations have very little correlation to the actual RGB values in the image. In fact, we know for a fact they have almost no correlation, because when you look at your partner at midnight in like on a in or in inside the house, or maybe in high noon outside, in terms of colors, it's completely different. It's got nothing to do with each other, right? But to you, it looks exactly the same. Like the brain just completely changes all the values to make the embedding exactly the same. So you see the same thing.
Yeah, I mean, a good example of this is to try to guess at how thick a wall is, an interior wall. Now, if you're a dad and you're constantly in the attic, fixing stuff, that's different. That's cheating. But like you might look at a wall and say, oh, that's maybe half a foot thick. But then when you actually look at a map, it's like, oh no, it's like 4 feet or something. Like it's just you'll be off by a ton, and yet you're able to navigate around your house, trivially. You don't have a map that is in any way accurate, but you have this really sort of deep, like semantic understanding of the different rooms and where to go. And so my older son sleepwalks, and so somehow he's able to sleepwalk down the stairs and into the fridge and like get a stick of cheese. Like I don't know how he does it, but he's able to do that. Yet there's that map isn't there, so it's all just these super deep embeddings. And because everything gets collapsed down to that, in the case of the human brain, million dimensional embedding, it's in a sense kind of easy to store, right? Because you're putting the same million numbers to hold everything you see, and to hold you might have to integrate over them for video. Audio might be a different thing, but it's all the data structure, if you will, is the same for everything.
So that actually, I think you nailed it. I think this is like it brings a very interesting topic, which is how do you even remember? How do you get like when your son sleepwalks? So when he looks at a stick of cheese and he knows it's a stick of cheese, or you looked at your loved one and they're whatever in high
A
noon
stick
or
of
when
cheese.
a stick of cheese. How do you know that a stick of cheese? No, how do you know it's the same thing?
Yeah.
You know,
Yep.
somewhere in your brain, you need to be able to go and match what you have against a bank of gobs of these like embeddings, right? And say, oh, this isn't a truck, this isn't a tree, and this isn't like whatever, like my grandma, and it isn't whatever, like a road. It's a stick of cheese, right?
Yeah, and even you can see really abstract like postmodern versions of chairs and still know right away it's a chair. Yeah.
Right. And so, how does that happen? How do you do that? And so, if you think about it, computers need to do the same thing. If I generate an embedding for a sentence, right? So you might think about, okay, I'm some whatever. Like I used to work on spam detection at Yahoo, right? So you see an email that looks like some Nigerian prince is trying to convince you to transfer money somewhere. You're like, okay, I know, okay, this I know what it is, right? But it's not exactly the same email. Like these scams look slightly different from each other, right? But any like rational person would like read this like, oh, I remember this thing. It's like looks like something else because in your brain you do this matching very easily. But computers don't know how to do this, right? So for computers, you would pass a different email that maybe semantically says the same thing, right? But like you would get a slightly different vector coming out of it. And unlike structured data, when you can do a hash table lookup and just fetch exactly the same key and then get the same value, you don't have that anymore. You just have a vector that's different than anything else you've ever seen before. It might be close to other things you've seen before or highly correlated with a small set, but it's not an exact match. And so if you went ahead and try to code this thing and try to say, okay, now I have a billion 1,000 dimensional vectors and give me the 100 that correlate the most with it, right? Except for going one by one, computing the correlation and just keeping the top 10, it's not clear what to do. And so now you get into this like really, really, really rich and interesting like topic in computer science that has to do with like vector indexes and retrieval. And that's something that like gets really deep really fast. And again, I'm happy to dive as deep as you want. I'm not sure how much you want to how much you want to scratch the
Yeah,
surface.
well let's go through sort of the life cycle of a system that uses vectors, right? So let's take like a recommender system, right? So we have let's say it's an image recommender system. So we have all of these images and whether the person liked them or not. And so we train some model based on that. And if a person likes two images, it's going to sort of bring those embeddings together. And if a person um, liked one image but not the other, it's going to pull them apart, right? And there's more complexity around random negative mining and all of that. We'll just leave all that alone and put a bookmark in that. But so you can imagine, in the beginning, it's all random. This is one thing that actually surprised a lot of people. In the beginning, all the embeddings are totally random. So, for any particular picture, it's just somewhere floating in that 1,000 dimensional space. And every picture is going to have some other spot. But then through this process of kind of pulling and pushing, pairs of points, together or apart, eventually it'll start to coalesce into that structure that we really like. And then to your point, if we know somebody, the last picture they liked was this one, then we can ask the question, what should we show them next? And it's, well, what are the closest things to that one they just liked, right? So now we have this problem of, here's a point, an embedding that we've trained. It could be maybe a week ago, but we have this trained model and we have this point that we know somebody likes. Let's get the points around it. And so, yeah, the naive way to do that is to go through every single point and say, how close are you? How close are you? How close are you? And then keep an array of the top 10. But, for something like Imagine Amazon. I mean, how many items does Amazon have in their inventory, right? Or how many pictures are on Instagram, right? I mean, just billions.
I actually know the answer to
Oh,
the
really? All right,
first
let's
one.
hear it. If it's not confidential.
I think it is.
Okay. Well, let's say it's more than 100 billion or something, at least for Instagram, right? There's so many people on there making pictures. And so, that whole idea of going one by one is you just can't do it. So that kind of gets to sort of what you've really been focusing on. And so how do people do that? I mean, Amazon works, Instagram, I can press F5 and it comes right up, every time I hit refresh, it's right there. I PTR, I pull down in the app and I get new photos. Like, how are people able to do that, in a reasonable time?
So now we basically are discussing this like algorithmic question, right? So let's just kind of make that
Yeah.
crisp of what the problem is. Okay, you get n vectors in dimension d. So n being large, say billions, d being large-ish but fixed, say 1,000. And now I give you another vector in dimension 1,000. I tell you, give me all the vectors that correlate the most with it. Or let's just say, maybe our closest in Euclidean distance. So I actually measure the sum of squared distances and sum of squared discrepancies on coordinates and take the square root of that. So like you said, yes, you can scan everything. Clearly, that's not feasible. So now how do you do it? Interestingly enough, you can actually prove that you cannot accelerate this beyond some limit, which is still pretty grim, okay, without incurring some level of error. In some sense, you need to accept the fact that you will have a little bit of approximation. So you might miss something that is, relatively close, maybe not almost identical, but kind of on the perimeter of the ball you're searching in. You might miss that, or you might accidentally include something that's slightly outside of it. So you have to accept a little bit of a fudge factor, right? But once you do, you can accelerate things significantly. And in fact, all the algorithms that do fast nearest neighbor search do approximate nearest neighbor search. Okay. Then approximate nearest neighbor search means look for the nearest neighbors, looks for the vectors that are closest approximately. Approximately means exactly what I said. There's like this little fudge factor around the edges. Okay.
Mm-hmm.
Now, I'll just kind of give a very quick and maybe almost like a sketch of kind of the main ideas in big algorithms. So first of all, there's clustering. Clustering is an obvious idea. I'll just start by saying I'll have like 1,000 clusters. Clusters are like a large collection of points that are all relatively close to one another. And instead of remembering all of them, I'll just kind of remember the center. Okay. And so when seeing something, I instead of thinking whether it's a mouse or a stick of cheese, I can first say, okay, is this an animal or like an inanimate object, right? If it's an animal, good. I've already reduced the search space by a big margin, right? So now I need to, and I can iterate on that. So you can like deconstruct the world.
That makes sense. Like hierarchical. Like for Amazon, if you search for batteries, there's probably something in Amazon that says this, don't bother with pet food. Like just forget that whole category. Like there's probably something, and then they can do something afterwards.
Right. And so, but even if you just take images, for example, even if with images, you can already take their embeddings and just already cluster things.
Oh, cluster the embedding space. You don't have to manually do anything.
Yeah, you cluster the embedding space. So now you take those points in high dimension, just say, oh, those set of points are so close together that instead of measuring all the distances, I can just measure the distance to the center. And if it's close enough, then I will maybe suspect that some of them should be close. Okay. And then I should check that. Okay. So how you cluster exactly and how you then search within those clusters is still, I still didn't talk about that, but kind of that's one main idea that works very well. And again, there's like a whole literature on how to do that fast and efficiently and accurately and so on. Then within each cluster, so now let's say you've narrowed down your search space from 1 billion to like, let's say 20 clusters, each one of them has 1 million points, right? Now they're not clustered anymore because they're all sticks of cheese, right? Mm-hmm. So maybe different, whatever, like
blue cheese.
Yeah, like a piece of chalk and a stick of cheese and I don't know. So now, like all white cylindrical things, right?
Yeah.
So now you really have to like do something a lot more refined, right? And there you have a whole another set of algorithms that look like what's called product quantization or other types of quantization. Instead of computing the dot product exactly, so saying I'll actually compute the distance exactly for like one candidate and one vector, I will compress it somehow and be able to just have a very quick, maybe of one, indication of is this like a likely match, right?
Hmm. So like a real simple way to do this would be just to have buckets, right? So you could just uniformly sort of divide the space up and say, if my point is so many buckets away from this point, then don't even bother, just skip that whole bucket or something.
Correct. I mean, buckets actually would be probably more akin to the clustering step,
Ah, okay, got it.
which is a good way. By the way, in low dimensions, bucketing and like an algorithm called KD trees is actually very efficient. If you have an algorithm, if your data is like 2 or 5 or 10 dimensional, then this like bucketing works fantastically well. In dimensions like 100 to 1,000, it kind of breaks spectacularly because high dimensional spaces are weird.
Yeah, that's true. I never thought about that, but yeah, I mean, just to give a bit of context, like for a KD tree, you can only split in. So a KD tree is a binary tree where at each node in the tree you split in one dimension. And you say everything that's more than this in that dimension, let's say you split where the fourth dimension is zero point 0.4 or higher. They all go to one part of the tree, everything else goes to the other part. But because each split is only one dimension, if you have 1,000 dimensions, you can't usually make very good splits.
No, I mean, if you split roughly in half, you only have log n splits before you remain with one item in every box. And log n could be like 10, I don't know, like definitely less than 50. And you have 1,000 dimensions. So that doesn't work. Yeah, so you have product quantization, which is like a very, very quick way of like iterating through those candidates. And again, a very mathematical, very, very cool field of research, has a lot of numerical and algebra in it, and high performance computing tricks, and it's very exciting. In fact, we actually have a paper coming out showing how we beat the state of the art on that, coming up in very shortly, in probably like a month or so. And then there's a whole field, there's a whole like other type of algorithms that kind of blend the two and kind of create this like graph over your points and say, okay, I'll traverse kind of the map, in high dimensional space. I'll have a set of candidates and I'll just look for the neighbor that gets me in the direction that I want to go, and I'll keep going that way. And again, those end up being very efficient sometimes, and sometimes kind of they just completely choke. And there's a lot of science about why and when that happens, and when they excel and when they're just kind of dead in the water. I can speak about this for many hours. I highly recommend, if you're a computer science major, if you're a mathematician, if you really care about high dimensional geometry, linear algebra, and so on, it's a wide and exciting field where a lot of cool things are happening. It's intimately related to how neural nets are applied and how data is represented. So very cool field.
Yeah, totally. Yeah. Yeah, I think that it makes a ton of sense. So the quantization, you're saying that through that you don't necessarily need a tree. You're able to get it so fast that once you have that cluster of a million items, you can get the dot product or approximation of the dot product over all million of them really quickly.
Correct.
Wow, that is so cool. Yeah, for some reason I totally didn't know that. I thought people were still using KD trees, but your point is spot on. I guess maybe just to continue the devil's advocacy, like what about ball trees or VP trees or these other things? Is the quantization just the fact that you can parallelize it maybe on a GPU or something? Does that make that more appealing than these other sort of tree ideas?
Yeah. So there are two factors that play in. One of them is the hardware, like you said. Like some algorithms just lend themselves really well to the kind of hardware that you have, so GPUs and so on, and also CPUs, just a memory hierarchy. I mean, the way it's set up, these efficient scans end up being surprisingly efficient. Uh, that's one. But the second thing is just like the weirdness of high dimensional space. We as humans, we are limited to like thinking about 3 dimensions. Like we talk about 4 and 100 dimensional spaces, but the mental image we have is really 3 dimensional. And high dimensional spaces are weird. I mean, they behave mathematically very, very, very different than low dimensional spaces. For example, you can ask yourself how many vectors that are exactly orthogonal to each other I can fit in a space of dimension D. Well, they're exactly orthogonal to each other, and so like they form like a coordinate system.
Right.
And so like in dimension D, you can only fit exactly D of those.
Yep.
Right. Well, what happens if I give you a little bit of flexibility and I say instead of exactly 90 degrees between two of them, you're allowed to have like 85 degrees between every pair. How many of those can you put together in dimension D? And so or maybe instead of vectors, I think about them as like lines. It's gonna go both ways, right?
I only know the answer for 2.
So in 2, you still can do only 2,
Yeah,
right?
that's right.
And so that didn't change. In 3 dimensions, you again can only do 3.
I guess so, right? Yeah.
And so somehow you would think that it would still grow linearly, and maybe at some dimension it would start growing a little bit more. But for most people, the intuition is that it would stay somehow linear in the dimension.
Yeah.
The interesting thing is that it grows exponentially in the dimension. So in dimension 1,000, you can have more vectors. You can have, I actually calculated once, I forget the number, but it was many billions of vectors that are all almost orthogonal to one another.
Wow, that is a remarkable. Wow, that's mind blowing. I want to really put an exclamation point on that. So, everything we're doing is an approximation, right? Everything. I mean, even the way you got these embeddings was through an approximation. You're using some kind of stochastic descent process. And so the fact that you're not at perfect 90 degrees, you're still effectively orthogonal with that tolerance. And so what you're saying is that there's billions of ways things can be just completely different from each other.
Yeah. In fact, I'll give you more than that. In fact, if you just take 2 random directions in dimension 1,000, they will be almost orthogonal.
Yeah. Yeah, I believe it. Yeah. Actually, that was a method, right? I mean, early on, before deep learning, random projections, where you just randomly assign vectors to documents, that was one of the ways that people were doing retrieval.
Correct. And in fact, my whole PhD was about how to do random projections like algorithmically faster.
Yeah, that makes sense. Wow, that is mind blowing. So, I see. And so then that explains the approximation, because I was putting a mental bookmark in that. Because if you do something like KD trees, you can do early stopping. Like at some point, that this partition, this entire subtree is further from the nearest neighbor. Even if I was to get the perfect point in this partition, it's still too far and I don't have to search anymore and I'm done. But because we're doing this clustering, and because there is a chance that maybe you're in between 2 clusters or something like that. It's just that it's because the clustering is centered around dense areas, the chance that you're not in one of those dense areas is like impossibly small, especially at these high dimensions.
Yes. So even though I think the last point you made was actually maybe the opposite of what I was saying. I mean, I think that you asked about KD trees and like balls and so on. Just maybe to explain to the audience. I mean, the idea is to say, okay, I'll have everything in one ball, and then I'll cover my space. I'll just take balls of radius like 1/2. Let's say everything lives in a ball of radius 1. I'll just cover my data in balls of radius 1/2, right? So everything lives in there, and then those 1/2 I'll cover with balls of radius 1/4 and so on, right? What I'm saying is that in high dimensional data, okay, if you have everything in a ball of dimension 1, if you had to cover your data with balls of radius 1/2, okay, every ball will contain 1 data point. There would be no tree. It would just like everything is far away from everything else, and so there's no tree, there's no structure. It's just like random chaos. And whether we like it or not, some data is sometimes like that.
How does clustering not suffer that same problem?
It does, and that's why vector indexes are hard to build, because in some sense, they are themselves like a model of the data.
Yeah, I see. So clustering. Oh, I see. I see. So maybe I'll try and get an understanding. So clustering is this coarse thing, but you really only have to do it once, and within a cluster, there's still many entries. Versus like this all these tree approaches, you're kind of doing a bad thing many times. Like as you're traversing this tree, you're making log n mistakes, until you get to the leaf.
Yeah. So I think again, it's hard. At least for me, it's very hard to like talk about this abstractly without kind of math and drawings and so on. So, but yeah, it's. I'll just maybe try to wrap it up by saying that it's a fascinating set of problems, which still have a lot of research going into them, and I highly encourage CS graduates and EE and anybody who's like into this thing and want to see some really gnarly math and really cool engineering. It's a good place to put some time in.
Yeah, totally. Yeah, I just want to double down on that. I think it's a really interesting. It's going to become it's becoming more and more important every day.
And it's the future of information retrieval. It's the future of how search engines and databases will work. And so like if you zoom out from the core index, it's like think about like in the analog of databases, like we've just spent whatever how 20-25 minutes just talking about B trees, right? Or if it's a search engine, we just spent 25 minutes talking about like an inverted index, right? But we haven't talked about the rest of the database around it. How do you do the embeddings? How do you save them? How do you retrieve from them? How do you do the all the
Yeah, the management system part of the DBMS. Yeah.
exactly? How do you update things in place? How do you read and write concurrently? How do you now like take this abstract algorithmic discussion and make like an actual hardened production database out of it that you can go and like do like image search on a billion images, right? In production and not worry about whether it will work or not.
Yeah, I actually had two questions, which I think we'll start to get into the management side of it. One was, how do you deal with the fact that when you retrain the model, even on the same data, unless you keep everything deterministic, which is almost impossible, if you retrain the model, the embeddings are totally different the next time. And so anyone who's using your database and storing the embeddings, for example, is going to be in a real big problem when you retrain, right? So how do you deal with that?
So for the listeners, Pinecone. So the company that I founded and ICO is called Pinecone, and it builds a vector database. That's what we do. Okay. Uh, the way we deal with this is we give our customers and our users full control over everything, right? We are not opinionated on like what embeddings you have, where how you create them, and when do you replace what with what. We actually give you full control over your data and how you retrieve from it and what your vectors are. And so we never actually like swap your vectors behind the scenes for you. So your query kind of looks one way a second later, it looks different. And you're sitting there thinking, what the hell just happened? If you train a different model and you create different embeddings, then you create like a new vector index in the database. And now you can decide which one of them you want to query. And maybe you phase one out and maybe you keep both of them, or you do whatever you want. And so, as a data infrastructure, we try to be the least opinionated and the most like enabling and just giving all the levers and buttons possible for our customers.
Yeah, that makes sense.
Yeah, I think what you're saying is again raises a lot of other very cool problems. If I just tweak, some portion of my data, like do I have to reindex everything? Do I have to like how does that work? Do I have access to like both versions of the index with some update and some not? If I tell me, oh, I just have all the vectors and I just move each one of them by a little bit, so all the data changes but not by a whole lot, can I somehow not just throw everything away and do everything from scratch?
Yeah, right.
There's so much to be done. I mean, this is like, and we've as a science and as an engineering community, we're not even remotely close to being able to answer those questions definitively.
Yeah, we have something in, so my background's in decision theory, and we have something in decision theory called actor regularized regression, or it could be called critic regularized regression. And what it's basically saying is, let's say it's a robot car. We'll train a model that copies what the robot car is doing right now. So this model, if the robot car maybe is being driven by a person, maybe it's not a robot yet, or who knows what it is, but maybe you have a lot of data of real cars, but we'll train a model that clones that behavior of these people or of this past system. And then when we go to train the model that's trying to maximize something, we regularize it, which means we add a penalty the further away it gets from this first model. And so I could imagine doing something like that, where if you keep your entire neural net that generated that embedding, then the next time around you can add some penalty so that the things won't drift too much. SGD is also like high dimensional spaces, where that sounds like it makes sense, and maybe for 99% of the time it makes sense, but there's still going to be 1% of the embeddings that are going to go to the moon, and so
Yeah, they're going to change completely, and again, that's fine. What we are trying to achieve is kind of make that layer as robust and just production ready as possible. So you, as a scientist or an engineer in a big company, if you want to do like semantic search over billions of documents or images or what have you, you get to care about your application, about how you retrieve and how you flow it to your customers and what they care about, what models you're using, and not like the entire everything we just talked about, like all the algorithms and the optimizations and the hardware and the distribution and the systems design, and like there's so much that goes into it that frankly you shouldn't care about if that's not your thing.
Yep.
Unless you're me, in which case that is your thing, and it's like,
Yeah.
it's the only thing you care about.
Yeah, so let's dive into that. So there's a bunch of people who are listening to this podcast and thinking this is the coolest thing I've ever seen or heard of in my whole life, right? And so tell us about Pinecone. Are there internships? Where are the internships located? Are there full-time positions? What's a day in the life of Pinecone? Kind of run us through Pinecone as a company.
So Pinecone, first of all, in terms of locations, we have centers in San Francisco, in New York, and in Tel Aviv, Israel.
Mm-hmm.
We certainly have open positions all across the board. I'll just gonna say the 3-4 most critical areas that we invest in. First of all, is the core engine. A lot of high performance computing, hardware accelerations, all the index stuff that sits mostly in Israel. All the cloud and scaling. Okay, so how do you take those indexes and those data structures and make them scale at cloud, built to billions of items and be consistent and persistent and highly available and so on. That sits mostly in New York right now. And another thing that sits mostly in New York right now is the management of it. So everything that looks like security, data governance, metering, logging, like all that stuff, right? So everything that makes it a managed stuff, like resource allocation and so on. Okay. And the last thing that we invest in is the machine learning. So the embeddings, the models, the applications of embeddings and vector, the representations in real life, and things like anywhere from recommendation to text to images to personalization to what have you. So it runs a pretty wide set of disciplines and applications, everywhere from low level C++, CUDA, and so on, all the way up to like modeling and so on. Of course, we have open positions both for interns and full time. Some of them are on our website, pinecone.io, and if you're interested and you're not sure that you appear in those open recs, just send us an email. We love hearing from people.
Cool. So what's a day like in Pinecone? So What's something that makes like Pinecone unique as far as a place to work? Do you have ping pong tournaments, or is there something that just kind of organically grew with Pinecone that is has been kind of sticky and interesting?
So COVID has really threw a wrench in a lot of that. But I will tell you what I feel is most exciting about working at Pinecone. And so for better or for worse, we've developed this addiction to like insanely smart, intelligent people, and it makes it very hard to hire people. But most of our folks have either PhDs or high degrees, ex AWS, Google, Facebook, Amazon, like built huge systems, architected like the internals of AWS and S3 and SageMaker and like Splunk and Databricks, and you know built unbelievable solutions for like whatever in the low level optimization kind of people who do like crazy,
Hmm.
just do crazy things. I mean,
Like SIMD and all of these things.
yeah, I've been in and around engineers my entire life, and like the sentence oh, I just made something like 3x faster is being said pretty casually.
Nice. That's
It's
amazing.
like what happens, like, oh yeah, I did this and that, and I changed here and I reorganized all of that. It's like, oh, now it's much faster. And I was like, oh shit. I had no idea that was possible. you know so you work just with people who just kind of mess with your brain. They're so smart and so talented, and it's just fun. And at the same time, it's just like I said, the problem itself is cool because it runs all the way from data and machine learning to like big gnarly systems design to low level algorithms, and kind of the whole thing needs to work as one unit. And so you kind of have to be very broad to really get it. And so it's just fun. It's just a fun place to work.
That makes sense. And I just wanted to end on this note. Who are the kinds of people who use something like this? Because I think some people might look at this and say, well, there's maybe a handful of companies in the world that have a billion images, right? But clearly, like even people who don't have maybe that much data, it's not just about not using a for loop. It's about the true management. I mean, you could use a CSV instead of MySQL if you don't have a big company. It doesn't mean that's a good idea, right? And so give us an idea of like, who is the sort of target audience for this, and like kind of how broad is that audience, and what are the different verticals there?
Yeah. So it's incredibly broad. I mean, you can, like you said, I mean, the fact that you don't have billions of objects, right? Even if you have 10 million objects, it doesn't mean you have to start building like a microservice for it. You'd rather, and the beautiful thing about consumption-based pricing for Pinecone is that you pay for what you use. And so if you have a small use case, it's going to cost you like $50 a month.
Yep.
So
Yep.
why are you even bothering? You know, so there's the whole like management aspect of it, which makes it like, you get all the bells and whistles, but you just get like the hassle-free experience, right? And that is already like a big enough market, right? But you get two different kinds of scaling issues that look very different systems wise. One of them is just like companies who have like an unbelievable amount of data, right? So they come to us say, oh, I have 10 billion items. Like, what the hell do I do now? Right?
Mm-hmm.
It doesn't fit anywhere. It's just going to cost me an arm and a leg to run anything, right? And companies who have a different scaling issue say, I have 10,000 queries per second. What the hell am I like?
Yeah. Yeah.
What do I do with this? So now I have this like super high availability, low latency system that I have to build. So I have to care about a whole different set of problems.
Yeah.
So being able to cater to all three is hard and exciting. And for somebody like me, who that's what I do for a living, that for me is a worthwhile challenge. But those kind of three quarter like buckets are, each and every one of them contains thousands of applications and different use cases. And so you don't have to be Pinterest or Facebook or Google to be facing these issues.
Yeah, I mean, one thing you hit on that I didn't think about until you mentioned it was the SLA, the latency, because I think
Yeah.
with PyTorch and TensorFlow and some of these things, you can do vector math without, like, I don't know anything about CUDA or OpenCL, or I've just heard these names, but I'm using PyTorch and it can do the job well. But I think that, PyTorch is not designed for low latency. And so if you have a million embeddings in PyTorch, you're stuck. Like, there's nothing that you can really do. You have to go outside of PyTorch to do that. And
Yeah, so you have to use something that's dedicated for it.
yeah,
And you have to optimize all the system around for it. I mean, we have POCs running with customers who use, a lot more than 10,000 queries per second.
yeah.
And they see a 15 millisecond P99.
Wow.
1.5.
Wow, it's
Yeah.
amazing.
And then, so for that, to get that, you have to, it's like the algorithms and so on, but you have to optimize, even like the way you deserialize JSONs. I mean, you can't be careless about that. It's like stuff like that you don't necessarily think about.
Yeah.
So it's like everything around it needs to be super optimized for this use case,
One last thing, actually, this is just, I don't want to get too much in the weeds here, but, like with MySQL, people do an insert statement, and it seems kind of, you're inserting these tuples, and so it kind of makes sense. So in your case, how do people dump, a billion embeddings into your database? I mean, is like, I guess the API it's still like a REST call with like a huge object that's attached to it or something.
I mean, you don't send all billion in one go. You probably would, you batch it and you send them in batches of 1,000, or you dump them on disk on S3 or GCS somewhere.
Oh, that makes sense. And so you have this S3 file that's massive that has all these embeddings, and you just point Pinecone to it.
Oh, it's like, hey, go digest this entire thing.
Yeah, that makes sense.
Or you can do it on the fly. You can do it like, you have a dynamic API. You can just upsert and update vectors like one by one or in batches.
Oh, that makes sense. Like, people are adding new products, and so you're
adding, deleting, updating, so on. Yeah.
So there's this, like, you're adding new products, and then boom, there's like a new embedding model. Everything has to get rewritten. So there's like now sort of this other snapshot that's being spun up, and then when that's ready, you flip them over, and then I mean, this is stuff that you do not want to do yourself. I've never done it. It just sounds brutal just talking about it. I mean, it sounds like a really exciting but hard to do.
Yeah, exactly. And we're not even scratching the surface. I think anybody who's built a distributed system, like you think about everything, and then a customer comes to you with like a mind bender and like, oh crap.
Yeah.
Like, they want to do what? So
yeah, cool. This is really, really awesome. So we have a link to Pinecone in the show notes. People check that out. Is there a free version for people like high school students or college students, or how can they get started with it?
So first of all, they can go to our website and they can start a free trial. The free trial right now is 2 weeks, and so it's not a whole lot of time. But if you're a student and you're working on a cool project and you want that extended, just drop me a note or whatever. We have a chat.
Cool.
Drop us a note and say, hey, I'm a student. I'm not really a customer, but I just really think it's neat. Can I keep using it? And odds are, if you really do something cool, we'll just let you do it.
Cool. That is amazing.
We've done that before, so we're all into education and supporting people's learning, kind of tinkerers building exciting demos.
Very, very cool. If people build anything really cool with Pinecone, let us know. Let Edo know. We'll have his contact, his Twitter, etc., the handle for Pinecone in the show notes. Thanks everybody for supporting the show on Patreon. We really appreciate that, and thanks for supporting us on Audible if you do that. And thank you, Edo, so much. This was an amazing episode. There's so much more depth we could go into. We could spend a whole day talking about embeddings. We didn't even get a chance to talk about the sort of machine learning part and ResNet and all of that. But that's we've done a really good job of covering the high level, and folks can definitely look up some of the things that we talked about and take it to the next level. Thank you so much.
Thank you.
Music by Eric Barndollar.
Programming Throwdown is distributed under a Creative Commons Attribution Share-alike 2.0 license. You're free to share, copy, distribute, transmit the work, to remix, adapt the work, but you must provide attribution to Patrick and I, and share alike in kind.